Every year, the world discards more than 92 million tons of clothing, enough to form massive fashion waste mountains. Yet, few people realize that this very pile of discarded textiles is quietly fueling a multi-billion-dollar industry. So how do thrown-away garments manage to embark on a journey of rebirth and return to store shelves? It begins at collection centers around the world, where heaps of used clothing are transported to large-scale recycling facilities. There, AI systems and workers sort them by material type and fiber structure. From there, the fabrics are cut into pieces, shredded into fibers, or chemically processed to extract raw materials. These materials are then spun into yarn, woven, and dyed once again, creating a new generation of textiles for the global fashion industry. Right now, let's join Agriculture Insight to explore how the fashion industry is attempting to transform one of the world's largest waste streams into the future of itself. Although it is widely seen as a solution to the fashion waste crisis, textile recycling is far from simple in practice. Many garments must go through a series of complex processes such as fiber shredding, chemical separation, cleaning, and re-dyeing, consuming enormous amounts of electricity, water, and energy. This becomes especially challenging with blended fabrics like cotton polyester, where separating individual fibers is far more complicated than recycling plastic or paper. Despite the enormous costs, the global textile recycling industry is still growing at an extraordinary pace. From recycled fibers and second-hand clothing to used garment exports and industrial materials, millions of tons of discarded textiles each year are generating tens of billions of dollars in value. This has driven countries such as China, India, and Sweden into a competitive race to develop recycling systems, treating it like the extraction of a new resource mine. Beyond traditional recycling, many brands are also embracing the trend of upcycling, transforming old garments into unique, high-value fashion pieces. From jackets made of reclaimed denim to handbags assembled from fabric scraps, what was once considered waste is now appearing on fashion runways and being sold at premium prices. It all begins with clothing donation bins placed in residential areas, shopping centers, and fashion stores around the world. Every day, tons of used garments are brought by people and dropped into these collection points instead of being thrown directly into landfills. Once the bins are full, specialized trucks continuously transport the collected clothing to large-scale processing centers. There, the items are first weighed and roughly inspected to separate those that are still wearable. Pieces that are too old, faded, or damaged are then sent onward to advanced recycling facilities. After the initial sorting process is completed, the remaining clothing is fed into massive hydraulic presses, where they are compressed into bales weighing hundreds of kilograms. These bales are then transported to specialized recycling plants, where the journey of transforming fashion waste into new raw materials truly begins. For items that are still in good usable condition, they enter the global second-hand clothing industry. After being cleaned, sorted, and packed, millions of tons of used garments from the United States and Europe are shipped in containers to Africa and Southeast Asia, regions where the demand for affordable clothing remains extremely high. Upon arrival, these bales of second-hand clothing, each weighing hundreds of kilograms, are delivered to massive used clothing markets, where tens of thousands of items are bought and sold every day. From t-shirts costing only a few tens of thousands of dong to vintage jeans and branded jackets, countless pieces that might otherwise have been discarded continue their life cycle instead of ending up as waste. Some shipments are even sold as mystery bales, meaning buyers have no idea what is inside until the package is opened. This treasure hunt experience has fueled the rapid growth of the second-hand market, especially among young consumers who are drawn to vintage styles and unique fashion pieces. But behind this bustling secondhand market, millions of tons of used clothing are still waiting to enter massive recycling facilities. There, they begin the most critical stage of the entire process: sorting. Inside these modern factories, artificial intelligence, color scanning cameras, and infrared sensors continuously analyze every garment moving along high-speed conveyor belts. Within just a few seconds, the system can identify fiber types such as cotton, polyester, wool, nylon, or denim, before automatically blowing each item into its designated processing stream. Alongside AI systems, hundreds of workers must still operate in constant coordination to check colors, fabric thickness, damage levels, and other details that machines may overlook. Because even a small amount of incorrectly mixed material can significantly reduce the quality of the entire recycled batch. This is also why textile recycling is far more complex than recycling paper or plastic. Most modern garments are made from blended fibers designed to improve elasticity, durability, and reduce production costs, making the separation of individual materials extremely difficult. After sorting is completed, used clothing moves on to the shredding and fiber separation stage. At this point, tons of fabric are cut into smaller pieces by massive industrial blade systems before being fed into high-speed shredders that break down the original fiber structure. In a short time, old t-shirts, jeans, and jackets are transformed into a thick, cotton-like mass of fibrous material. This becomes the key raw input for the next stages of recycling inside the plant. However, with each recycling cycle, textile fibers become significantly shorter and weaker compared to their original state. This also means clothing cannot be recycled indefinitely, as repeated processing eventually reduces fiber quality to a level that is no longer strong enough to produce new garments. For this reason, many factories often need to blend in virgin fibers to the recycled material in order to maintain the durability of the final products. After the shredding stage, the resulting fiber mass is sent to a cleaning system designed to remove dust, loose threads, zippers, buttons, and any remaining contaminants within the fiber blend. In many modern facilities, industrial magnets, high-pressure airstreams, and automated filtration systems operate continuously to separate metals and other unwanted materials from the textile fibers. For certain garments made from heavily blended materials, the process becomes even more complex, as they may require chemical treatments to separate individual fiber types before recycling can continue. This is also considered one of the most complex and energy-intensive stages in the entire textile recycling process. After cleaning, the fiber mass is sent to the spinning stage, where piles of discarded clothing gradually begin to return to the form of a completely new raw material. Since the fibers produced after shredding often retain the original color of the fabric, many factories can directly take advantage of tones such as black, gray, or denim blue without the need for full re-dyeing. This significantly reduces water usage, chemical consumption, and energy demand throughout the recycling process. Meanwhile, white textiles are considered the most versatile material in the recycling industry, as they can be dyed into almost any color afterward. For this reason, white fabrics are often more valuable and are carefully separated from the very beginning of the sorting process. After the spinning process is completed, the massive rolls of recycled yarn are transferred to weaving factories, where they are transformed back into finished fabrics. At this stage, thousands of threads are interlaced by high-speed industrial looms, producing continuous rolls of fabric for the fashion industry. Depending on the type of fiber and weaving technique, these recycled textiles can be turned into t-shirts, hoodies, towels, or even various industrial materials. However, denim is considered one of the most distinctive materials in textile recycling. Unlike many other fabrics, used jeans often retain their characteristic indigo blue color even after being shredded and respun into new fibers. As a result, many factories can continue weaving them into new denim without extensive re-dyeing. On specialized weaving machines, thousands of blue threads are continuously interlaced to recreate the thick, durable structure typical of denim fabric. This ability to preserve its original color has made recycled denim one of the most important directions in sustainable fashion, especially considering that producing a single new pair of jeans can consume thousands of liters of water. For white or very light-colored fabrics, they are typically sent to the dyeing and finishing stage. This is where recycled fabric rolls begin to take on a completely new appearance before returning to the fashion industry. Inside the factory, massive rolls of fabric continuously pass through industrial dyeing systems, stretching tens of meters long, where dyes are deeply absorbed into each fiber under carefully controlled temperature and pressure conditions. Depending on the final product, the fabric may then undergo additional treatments to enhance softness, improve elasticity, reduce wrinkling, or create various surface effects. Once completed, these recycled fabric rolls are cut, sewn, and transformed into a wide range of new products, such as t-shirts, hoodies, handbags, and fashion garments, completing the journey of turning once discarded clothing into entirely new creations. For recycled denim, the journey does not end after it has been woven into fabric. The newly produced denim rolls are then sent to the finishing stage, where they gradually take the shape of familiar jeans seen in the market. At this stage, the fabric is cut, sewn, and surface treated to create faded effects, distressed textures, or signature vintage styles. Many modern factories even use laser technology to etch patterns and create highly precise fading details on the surface of the jeans. Once completed, these recycled denim products continue to appear in fashion stores around the world, where few people realize that they once began as discarded pairs of jeans dropped into donation bins. However, despite the rapid growth of the textile recycling industry, the global volume of discarded clothing continues to rise at an enormous pace. One of the biggest driving forces behind this trend is the explosion of fast fashion. With brands such as Shein, Zara, and H&M, new collections are released every few weeks, fueling a non-stop cycle of consumption. Low prices, TikTok trends, haul videos, and micro-trends have made wear once culture increasingly common. People buy clothes just for photos, viral trends, or short-lived bursts of excitement. This pace of consumption is creating unprecedented environmental pressure. Polyester clothing, when washed, can release thousands of microscopic plastic fibers into rivers and oceans, making it one of the largest sources of microplastic pollution today. At the same time, industrial dyeing processes discharge vast amounts of wastewater containing toxic chemicals and heavy metals. All of this combines into a single outcome. Millions of tons of clothing are discarded every year, turning many regions of the world into massive fashion graveyards that far exceed the capacity of current waste management systems. A striking example is the Atacama Desert in Chile, considered one of the world's largest dumping grounds for discarded clothing, or Contamonto Market in Ghana, a massive second-hand hub in West Africa, where continuous inflows of used garments eventually still end up as waste. As the problem continues to intensify, the fashion industry has begun exploring a completely different direction, turning to nature as a new source of materials for the future. From bamboo fibers, seaweed, and mycelium fungi to pineapple leaf fiber, hemp, and fruit byproducts, materials once considered waste are now being tested to create new types of textiles. However, in reality, these materials are still far from mainstream adoption. The vast majority of clothing today is still produced from cotton and polyester, the two dominant fibers in the global fashion industry. As a result, so-called eco-friendly materials currently play a supporting role rather than serving as a full replacement. From discarded garments that once seemed worthless, textile recycling technology is opening a new life cycle for fashion, where waste does not disappear but is reborn into new products, continuing to circulate within the ever-evolving world of fashion. A little-known fact: most clothing in the world is not made from natural fibers, but from plastic, primarily polyester, which accounts for about 70% of the global market. More strikingly, the raw material for this fiber often begins as discarded plastic bottles. Before being transformed into fabric, plastic must pass through the sorting stage, a critical step that determines the overall quality of the output. Although there are theoretically 7 recycling codes, in practice only PET and HDPE are clean and valuable enough to be reprocessed. In modern facilities, rotating drums, screening systems, and optical sorting robots work together to remove dirt and impurities, accurately separating materials with high efficiency. The selected plastic bottles are then shredded into small flakes, thoroughly washed, and processed through float sink separation to eliminate unsuitable materials. These flakes are melted, filtered through ultrafine screens, and cut into millions of plastic pellets per hour, an intermediate raw material used across various industries. From here, the pellets are reheated and extruded through spinnerets with microscopic holes, forming filaments finer than human hair. These fibers are rapidly cooled, stretched to enhance strength, and wound into yarn, serving as the foundation for polyester fabrics found in clothing, backpacks, and countless consumer products. The entire process represents a remarkable transformation, turning plastic waste into high-value textile material. However, its downside is becoming increasingly evident. During use, especially when washed, polyester fabrics release microscopic plastic particles into wastewater, which eventually flow into rivers and oceans and ultimately return to the human food chain, raising significant concerns about the true sustainability of the industry. Considered one of the rarest textiles in the world, lotus silk is not only astonishing for its price, up to $2,000 for a single lightweight scarf, but also for the extraordinary way it is made. During the lotus season, stems are harvested directly from cultivated fields and natural ponds, then thoroughly washed and left to dry. The stems are carefully sorted into leaf stalks, flower stalks, and seed pod stalks to facilitate fiber extraction, spinning, and weaving. Before extraction, each stem must be cleaned meticulously. During the process, the fibers are often wiped with clean water to preserve their natural pale color. To produce lotus fiber, artisans delicately cut each stem, then swiftly pull, twist, and join the fine filaments into continuous threads. These fibers are extremely thin and soft, requiring exceptional hand skill. Each strand must be drawn and connected seamlessly as the process continues. A skilled worker can handle around 260 to 280 stems per day, yielding approximately 150 to 170 meters of thread. Notably, every stage is performed entirely by hand, with fiber extraction being the most critical step. Once extracted, the fibers are wound onto spools and spun to increase strength before being transferred to a loom, where thousands of fine threads are woven together into finished fabric. The final product carries a subtle herbal fragrance, combining the softness of silk with the breathability of linen. What truly sets lotus silk apart is not just its high price, but the fact that behind each delicate piece, lies hundreds of lotus stems and countless hours of meticulous craftsmanship. Did you know that one of the best insulating materials on the planet doesn't come from a laboratory or a high-tech factory? It comes from the nest of a sea duck, capable of retaining warmth in temperatures as low as -40 degrees Celsius. It's so rare that a blanket made from it can cost as much as a Toyota Camry. But what truly makes this material remarkable isn't just its thermal performance, it's the almost unimaginable journey required to obtain it. During each breeding season, female eider ducks pluck the softest down from their own bodies to line their nests and protect their eggs. Once the birds leave, collectors search for these nearly invisible nests hidden among grass, rocks, and seaweed. Each nest yields only about 15 grams of down, so light that even a sea breeze can carry it away. And that's only the beginning. What's collected is mostly a mixture of twigs, seaweed, and coarse feathers. Hours of painstaking work follow, as each strand of down is hand-picked, sorted, and meticulously cleaned. The clusters are then fluffed to assess cleanliness, loft, and down content. Once they meet the standard, they are carefully filled into small compartments within high-density cotton shells. Remarkably, just 1 kilogram of this down can contain over 1 million fine filaments, and a single nest is enough to begin the creation of one of the most naturally efficient insulating materials in the world. Over 5,000 years ago, while the pyramids were still under construction, humans had already learned to weave fabric from plant stems. That fabric was linen, one of the oldest textiles ever used, famously wrapping the bodies of Egyptian pharaohs. As summer reaches its peak in June, flax fields enter the most critical stage of their growth cycle, the harvest. Specialized machines move straight into the fields, where gripping mechanisms seize each row of flax and pull the plants directly from the soil. The stalks are immediately transferred onto conveyor systems, aligned in parallel, and spread evenly across the field in neat rows to dry naturally, while the seed heads are separated through suction systems. Within minutes, the entire field appears reprogrammed into orderly lines, marking the beginning of one of the world's oldest textile processes. After 2 to 4 weeks of field drying, when moisture levels drop to the ideal range, the flax is collected and transported to the factory. There, mechanical processing begins with continuously rotating rollers that break the tough outer layer. Next, high-speed scutching systems, operating at thousands of darbs per minute, remove nearly all of the woody core, leaving behind only the valuable long fibers. These fibers then pass through combing stages with hundreds of steel pins, aligning them, removing impurities, and sorting them by length, an essential factor that determines the fineness of the final fabric. Finally, the fibers are spun into yarn and fed into high-speed looms, where tens of thousands of warp and weft threads interlace with precision to create linen, a fabric known for its exceptional durability, natural breathability, and, despite having a coarser surface than cotton, a lifespan that can be up to 5 times longer under real-world conditions. At the next stop, we arrive at vast fields of white cotton, where not only soft fabrics are created, but also a key component of US dollar bills, turning an agricultural material into part of the physical foundation of currency. From the field, the entire process operates like a massive industrial system. Round module harvesters move continuously, using rotating drums fitted with metal spindles to carefully separate cotton fibers from plants standing 1 to 1.2 meters tall without damaging them. The cotton is immediately suctioned into the machine, transferred to a rear chamber, and compressed directly into cylindrical modules about 2.5 meters in diameter, each weighing up to 2 tons. Right in the field, every module is wrapped to protect it from moisture, effectively transforming the entire field into a closed-loop production system from the moment of harvest. After harvesting, raw cotton is compacted into bales and transported to spinning mills, where this natural material enters a precise industrial processing chain. Once the bales are opened, high-speed rotating drums combined with strong airflow fluff the fibers, remove dust, and blend them for uniformity. The cleaned cotton then passes through carding machines equipped with hundreds of steel pins, aligning the fibers into a continuous sliver. These slivers are stretched, layered, and stabilized before being lightly twisted into roving. In the final stage, spinning frames operating at around 20,000 RPM draw and tightly twist the fibers into finished cotton yarn, ready for weaving. From a seemingly simple crop, cotton has become a global fiber source, accounting for about 25% of total production. Yet behind its widespread use lies a significant cost. A single t-shirt can require up to 2,700 liters of water, and although cotton occupies only 2.5% of agricultural land, it consumes nearly 16% of the world's pesticides, highlighting a major paradox of the modern textile industry. Once discarded in fields after harvest, few would expect that inside sharp pineapple leaves lie ultra-fine, nearly invisible fibers, delicate enough to be woven into piña fabric, one of the most valuable traditional textiles, priced at up to $300 per meter. When pineapples are harvested for global consumption, the long, spiky leaves are typically left behind as agricultural waste. However, for many farmers, these leaves are a valuable raw material for producing piña fabric. The leaves are cut using specialized knives, then fed into decortication machines to remove the fleshy layer and expose fine cellulose fibers running along the veins. These fibers are washed multiple times to eliminate sap, then sun-dried for 2-3 days until they become dry, lightweight, and naturally lustrous. Once stabilized, the fibers are combed straight, sorted by length and fineness, and twisted into threads before being transferred to a loom. There, warp and weft threads are carefully interwoven to create a fabric known for its exceptional lightness and breathability. Notably, producing just 1 meter of piña fabric requires around 80 pineapple leaves, and high-end handcrafted pieces can take over a month of meticulous labor, transforming agricultural waste into one of the most refined textiles in the world. Amid the massive ocean currents of the North Pacific exists a region containing trillions of pieces of plastic swirling endlessly for decades, covering an area of approximately 1.6 million kilometer squares, or roughly 3 times the size of France. And the world does not have just one, but as many as 5 gigantic ocean garbage patches like this. These are not solid floating islands of trash as many people imagine, but rather a plastic soup dispersed across an enormous area where ocean currents continuously gather plastic from all over the world. But the real danger does not lie in the massive pieces of plastic visible to the naked eye. It lies in the process by which they are continuously broken down by sunlight, ocean waves, and friction over many years until they become nearly invisible microplastics. These particles then enter the marine food chain and eventually return to the human body itself. In ecological logic, every year of delay in cleanup means all future intervention efforts become more complicated and expensive. But humanity delayed that process for more than 7 decades, ever since petroleum-based plastics began exploding on a global scale in the mid-20th century. Scientists estimate that this region accounts for only about 1% of the world's ocean water, yet contains up to 7% of all floating surface microplastics globally, equivalent to around 1.8 trillion pieces of plastic with a total mass reaching 100,000 tons. For many decades, experts almost unanimously agreed that cleaning this area was impossible. Estimated costs reached tens of billions of dollars, and using traditional methods such as ships and nets, the process could take thousands of years. But right in the middle of what seemed like a hopeless situation, a bold idea began to emerge. Instead of chasing plastic across millions of square kilometers of ocean, humanity would let the ocean currents themselves concentrate the waste in order to capture and transport it into massive industrial processing systems before it permanently degrades into microplastics. It was an approach that went against conventional intuition, yet perfectly aligned with the way the ocean itself operates. And to turn that seemingly irrational idea into reality, a 16-year-old Dutch boy named Boyan Slat emerged with an approach completely different from every ocean cleaning method that had existed before. 1 year after a disappointing diving trip off the coast of Greece, where he saw more floating plastic bags than fish, in the fall of 2012, at the age of 18, Boyan Slat stepped onto the TEDx Delft stage with an 11-minute talk titled, "How the Oceans Can Clean Themselves."
However, I believe the Great Pacific Garbage Patch can completely clean itself.
For months, Slat's seemingly naive question received almost no attention and gathered only around 2,000 views. But by February 2013, when technology and environmental media outlets began discovering it, everything changed almost overnight. Donations quickly started pouring in, forcing Slat to make the biggest decision of his life: continue pursuing his aerospace engineering degree or drop out of university to chase the ambition of cleaning the oceans. At the time, his bank account contained only around $300 in savings. Slat chose the ocean. Just days after the video went viral, the project received approximately $90,000 in donations. And by September 15, 2014, the total had reached $254,282, becoming the most successful non-profit crowdfunding campaign in history at that time. And from that moment on, in order to prove that the oceans could truly clean themselves, the Ocean Cleanup was officially born, with its first mission keeping millions of pounds of plastic stationary in the middle of the ocean. The Ocean Cleanup first had to solve an extremely complex physics problem: how to create a structure light enough to continuously float on the ocean surface, yet durable enough to withstand large waves, ultraviolet radiation, salt water, and mechanical stress for years in the open sea. The system's greatest distinction lay in its gigantic mechanical structure, designed as a U-shaped floating barrier approximately 600 meters long. To create this structure, the Ocean Cleanup used around 50 sections of high-density polyethylene pipe, each nearly 1.2 meters in diameter, a material commonly used in offshore oil and gas systems because of its corrosion resistance, impact durability, and ability to maintain stable buoyancy in harsh marine environments. Most importantly, the assembly joints were built using steel connectors, reinforced cables, and flexible linkages that allowed the entire structure to bend with the motion of the waves rather than resist them. Beneath the floating pipes, engineers installed a 3-meter-deep skirt made of technical fabric. This depth was carefully calculated to retain most plastic floating near the surface, while still allowing marine life to swim underneath, reducing the risk of harming the ecosystem. The operating principle of System 001 was based on a very small difference in movement speed between the system and the plastic waste. While floating plastic is pushed faster by wind and waves, Wilson generates greater hydrodynamic drag, causing it to move slightly slower and gradually funnel debris into the curved central section like a gigantic floating trap in the middle of the ocean. In September 2018, System 001, nicknamed Wilson, was officially towed out of San Francisco Bay to begin its first real-world test in the largest garbage patch on Earth. However, the system quickly revealed serious limitations. Unstable ocean currents and inconsistent drifting speeds prevented the system from keeping plastic concentrated inside the barrier, causing much of the debris to escape back into the ocean instead of remaining trapped for collection. By the end of 2018, An 18-meter section fractured due to material fatigue at welded connection points, forcing the system to be towed back to Hawaii after collecting only around 4,000 pounds of plastic in 4 months. The figure was far below initial expectations. As a result, System 001B was introduced in 2019, an upgraded version designed specifically to solve the problems that had caused Wilson to fail. Beneath the system, a parachute-style floating anchor approximately 6 meters long creates additional hydrodynamic drag, allowing the entire structure to move about 0.3 to 0.5 meters per second, slower than the floating plastic on the surface. This very small speed difference is enough for tens of thousands of plastic fragments to continuously accumulate in the central area while retaining thousands of pounds of waste during each collection cycle. After around 6 to 8 weeks of operation at sea, the plastic accumulated in the center of the system is lifted onto the support vessel using industrial cranes. On the ship's deck, workers begin preliminary sorting of fishing nets, hard plastics, large containers, and organic contaminants before all the plastic is packed into containers and transported to recycling facilities. This process is extremely difficult because much of the plastic has drifted through the ocean for years, exposed to saltwater, UV radiation, and marine organisms that degrade and contaminate the material, making sorting and recycling far more complex than conventional land-based plastic waste. Its composition is also astonishing. Fishing nets account for 46% of the total mass, while between 75% and 86% of the plastic originates from offshore fishing activities. After more than 10 upgraded versions since System 001 Wilson, by 2025, the ocean cleanup had removed more than 25,000 tons of plastic waste from river systems and oceans worldwide, equivalent to the mass of tens of thousands of gigantic Labubu figures being pulled back out of the sea. But the ocean cleanup quickly realized that cleaning the oceans alone was not enough, because around 1,000 rivers, representing less than 1% of the world's river systems, are responsible for nearly 80% of the plastic continuously flowing into the oceans every year. Among them, Thailand, China, Indonesia, the Philippines, and Vietnam alone release as much ocean plastic as the rest of the world combined. This discovery changed the nature of the problem itself. Instead of focusing solely on cleaning up plastic that had already drifted into the ocean and dispersed across millions of square kilometers, the organization shifted toward a strategy of intercepting plastic at highly concentrated entry points, where river flow and geometry allow for far more efficient intervention in terms of energy and cost. From this logic, the interceptor system was developed as an automated river plastic collection platform. Each system is approximately 24 meters long, nearly 16 meters wide, and permanently anchored along riverbanks using heavy-duty piles and tension cable systems. Extending from the interceptor's main body, a floating barrier stretching dozens of meters is positioned diagonally along the direction of the current to continuously guide floating waste toward the central intake opening. As debris approaches the system, an automated conveyor belt approximately 1.5 meters wide begins operating, continuously lifting plastic from the water surface into the vessel. The entire system operates on solar energy, using around 32 solar panels installed on the roof to power the conveyor belts, sensors, and AI systems that monitor waste flow in real time. One of the most notable projects in the United States is Interceptor 007, deployed on the Los Angeles River, one of the most plastic-polluted urban rivers in America, where more than 220,000 pounds of waste were intercepted within the first months of operation before reaching the Pacific Ocean. But pulling millions of pounds of plastic back out of rivers and oceans was only the beginning. The next challenge was how to transform that chaotic mass of waste into reusable industrial raw materials on a massive scale. More than 4,000 years ago, in ancient Mesopotamia, humans accidentally created one of the most influential inventions in history: soap. By boiling animal fat with wood ash, they discovered a compound capable of washing away dirt, laying the foundation for the concept of hygiene, a core element of modern medicine. From the Roman civilization to the Arab world, that early formula continued to be refined, with the addition of plant oils, gradually entering the industrial era in Europe. For thousands of years, soap has quietly served as a protective shield against disease, a simple yet enduring invention that has accompanied the development of clean and progressive civilizations. Now imagine just a single day without soap. Within only a few hours, countless bacteria could cling to the skin without us even noticing. Soap is what prevents that scenario. When mixed with water, its molecules break down the lipid membranes surrounding bacteria and viruses, causing them to disintegrate and be washed away. This seemingly simple chemical mechanism has helped save billions of lives, from 19th century cholera outbreaks to modern-day flu pandemics. Therefore, soap is not merely a common cleaning product, but the most fundamental and essential line of defense humanity has against the invisible microbial world. The refined sunflower oil is then pumped into the reaction vessel, the heart of the entire production line, where the most critical stage takes place, the saponification reaction. This is the chemical reaction between vegetable oil and a strong alkali, typically sodium hydroxide (NaOH), producing two main products: soap, the sodium salts of fatty acids, and glycerin, a natural humectant that helps keep the soap bar soft and gentle on the skin. Thanks to its high content of oleic acid and linoleic acid, sunflower oil allows the reaction to proceed steadily, resulting in fine lather and a light texture. The oil is heated to approximately 140 to 160 degrees Fahrenheit before the NaOH solution is introduced under carefully controlled pressure. A twin helix agitator system operates continuously to ensure thorough mixing of the oil and alkali molecules. Sensors continuously monitor pH, temperature, and electrical conductivity to prevent excess alkali, a factor that could cause skin irritation. As the reaction nears completion, the mixture begins to thicken and changes color from pale yellow to creamy white or light brown, depending on the type of oil used. In the final mixing stage, natural pigments such as clay, activated charcoal, or turmeric powder are added to color the product while the soap mass remains warm. The crude soap is then separated from the glycerin solution and washed with brine to remove impurities before being transferred to the neutralization area. Although this process originates from techniques developed thousands of years ago, precise control of temperature, timing, and reaction ratios remains decisive in producing high-quality sunflower oil soap, smooth, mild, and safe for the skin. After neutralization, the crude soap is cooled and then ground into small pellets, known as soap noodles. These pellets are fed into a twin-screw mixer, where two counter-rotating shafts continuously knead the material to create a pliable, uniform texture. During this process, glycerin is added to maintain natural moisture, purified salt increases hardness, and natural essential oils such as lavender, bergamot, orange, or peppermint are sprayed directly into the mixing chamber to create distinctive fragrances. If color is desired, natural mineral pigments such as red clay or activated charcoal are incorporated at the final stage. All parameters, including temperature, viscosity, and mixing time, are strictly controlled to ensure that fragrance and color are evenly distributed throughout the entire soap mass. The result is a smooth, soft soap base with stable structure, ready for the subsequent shaping stages. After the blending process is complete, the smooth and pliable soap mass is transferred to a vacuum plotter, a machine responsible for compressing, deaerating, and homogenizing the material before shaping. Inside the extrusion chamber, A rotating screw continuously pushes the soap forward under high pressure. In the middle section of the machine, a vacuum chamber operates to completely remove microscopic air bubbles and trapped air pockets within the mixture, ensuring that the extruded soap becomes dense, solid, and perfectly smooth on the surface. Once stable pressure is achieved, the soap is forced through a steel die fitted with dozens of small concentric round openings. Under strong compression, the material is extruded into soft, uniformly colored strands, an indication that plasticity and moisture content have reached ideal levels. These strands are continuously collected on a conveyor belt, gently cooled and prepared for milling or a second extrusion to further increase density and uniformity. The vacuum extrusion stage not only provides the soap's initial form, but also determines the product's physical integrity. If pressure or vacuum levels are not precisely controlled, the finished bars may develop voids, cracks, or breakage during drying. For this reason, all pressure sensors and screw speed control systems are regularly calibrated to ensure absolute stability before the soap proceeds to the next stage. After the vacuum extrusion stage, the dense and uniform soap mass is continuously pushed through the die head, forming long bars with either circular or rectangular cross-sections. To ensure that each bar meets the exact standard dimensions required for stamping, they are conveyed to an automatic cutting machine. Here, rotating blades slice the soap bars to a pre-programmed length. An optical sensor system continuously monitors the position and movement speed of the soap bars, synchronizing the cutting blades with the extrusion rate. This precision is crucial. Even a slight deviation or a cut that is not perfectly perpendicular can prevent the bar from fitting properly into the stamping mold, leading to defects in later stages. Each cut piece is randomly inspected for weight, squareness, and surface flatness. Products that fail to meet the standards are collected and returned to the mixing stage for reprocessing, ensuring optimal material utilization and consistent quality throughout the entire production line. When the soap bars emerge from the vacuum plotter, they form continuous strips that must be divided into smaller sections before being placed into molds. This step is carried out using either automatic or semi-manual cutting systems, depending on the production scale. In industrial lines, high-speed rotating blades are fully synchronized with the extrusion rate, ensuring that each soap segment has precise length and weight. In smaller workshops, operators may use mechanical cutters controlled by a foot pedal, a solution that still ensures accuracy while allowing better control over the cut surface. Immediately after cutting, the soap billets are pushed into metal molds by a pneumatic piston inside a hydraulic stamping machine. The powerful compression force from the hydraulic system tightly compacts the soap mass, eliminating internal voids and shaping the surface according to the mold design. This is a crucial transformation step, turning freshly cut segments into solid, uniform blanks, ready for the final shaping stage and brand logo stamping. When the freshly stamped soap bars are still soft, they move to the logo engraving stage, the step that creates a distinct brand identity for each product. Depending on the scale of production, this process may be carried out automatically using a logo stamping machine or manually with handheld molds. In large industrial production lines, steel dies engraved in relief or intaglio are lightly heated and then pressed onto the soap surface using a pneumatic piston, producing sharp and consistent imprints. In smaller artisanal workshops, craftsmen use handheld brass or steel stamps, pressing them directly onto the soap bars with controlled force. This method creates subtly unique products. Each bar may vary slightly, yet all carry a refined individuality and characteristic handcrafted value. After logo engraving, the soap bars undergo careful inspection through an optical camera system combined with manual evaluation. Technicians assess the depth and sharpness of the logo, while also checking surface smoothness, color consistency, and gloss, to ensure that every product meets aesthetic and quality standards before moving on to the final finishing stages. Products that meet quality standards are transferred to the final sorting and packaging line, ready to enter the market. After passing inspection, the finished soap bars move into the automated packaging system. Before wrapping, they are gently cooled with a stream of dried air to stabilize their structure and preserve their fragrance. Next, each bar passes through a wrapping machine using film or waxed paper, where the packaging is heat-sealed at a controlled temperature to ensure a tight seal without deforming the product. Depending on brand positioning, the packaging may consist of craft paper, branded printed paper, or transparent BOP film. All packages are automatically cut, labeled, and printed with batch codes, production dates, and origin information. The packaged soap bars are then placed into moisture-resistant carton trays, sealed with inspection labels, and transferred to storage for shipment. This final stage completes the entire production line, the moment each soap bar leaves the factory in its finished form, ready to reach consumers.